Hi. Right, our next paper is presented by Alex Hazle and James Towers. Alex graduated from Lancaster University with a first-class degree in mechatronics and having won awards for his dissertation. He started his career at Trio Motion Technology, where he spent 7 years in industrial automation, developing software and electronics, as well as supporting machine builders worldwide. He currently sits within the architecture team. In his current position, Alex actively started to pursue systems engineering methods to deploy a function design and development process. He has now been a member of INCOSE for 2 years and regularly participates in the MBSE working group and automotive interest group. James Towers has had a varied degree in software and systems modeling and has presented both papers and tutorials at conferences and seminars, as well as writing and delivering training courses on the subject. He has produced consultancy training and mentoring to various organizations working in automotive, consumer electronics, defense, finance, information technology, power electronics, telecoms, rail, retail, and supply chain. He is a chartered engineer, an OMG certified UML professional, and member of the IET and INCOSE UK, where he is chair of the UK Model-Based Systems Engineering Working Group. He's also a visiting lecturer in MBSE at the University of Warwick. So that's right. So we'll hand over to James for their presentation. Thank you.
Thank you, Malcolm, and good morning, everybody. We're going to be sharing the presentation duties this morning. So I'm going to start off. I'll then hand you over to Alex and then back to me for a wrap up. Not surprisingly, model verification and validation is one of the obstacles to the adoption of model-based systems engineering. It's very easy to create a model, but how do you know if it's then complete consistent? One of the pitfalls that can happen is that you can train people in how to produce models. They can be experts in languages such as SysML. They can go away, sit in the corner and produce a very complicated and detailed model. And in fact, it might be very useful to them. But then how do you get the rest of the engineering endeavor to get involved in the model and to check that it does in fact reflect the requirements and in fact meet the requirements of the stakeholders? Our investigation today is going to focus on MBSE using SysML. However, we believe that the advice we're going to give here is applicable to model-based systems engineering using any language. There may be a few SysML specific things, but we believe there are equivalents in other languages as well. If you were to start an investigation into model verification and validation in model-based systems engineering, you'd probably go to the usual sources, to the definitive volumes on the SysML language. You'd probably think these were Dalgety, Friedenthal et al. And Wilkins. And if you're a bit more interested in the adoption of model-based systems engineering and its application, then you might look at Holt and Perry from 2018. What you'll probably notice in these books is, while they do mention the fact that you need to perform V&V on the model, they don't really go into a lot of detail. There are fewer books actually talking about model verification and validation in general. There are a few notable exceptions, Dibabi et al. And Lang et al. But 2 out of the whole field doesn't really seem a lot. And you'll also notice if you read these books that they're very academic. So we felt that there was a little bit of a gap really in the whole subject of model V&V, and hence the need for this investigation. On the other hand, there are a large number of papers relating to MBSE model verification and validation, and these can be broadly categorized into from Douglas 2005. They are semantic review, which is essentially reading the model and checking that it conforms to the modeling standard or to the language standard or to any architecture framework that you're using. You then get papers relating to model testing. Naturally, these relate to simulation of the model. So if the model is simulated, if it can be interpreted, does it behave in the way you expect it to behave? And then third of these techniques are what are known as formal methods. Formal methods tend to be around analysis, which are mathematical and other methods of proving that the model is complete and correct and does what you expect it to do. There's pros and cons for each of these methods. But again, most of the literature on this seems to be quite academic, and there doesn't seem to be very much practical advice about how you would go about doing it. The good news is that there are some parallel disciplines where we can also take lessons from. So if we take the parallel discipline of model-based software engineering, publications such as Unhelke and Vigas, then these talk about how do you go about doing model-based V&V in the software domain. You can also look at the similar domain of requirements engineering. If you think of a requirement set as also being a model, then publications such as Young and Gottesdiener also talk about these important things of model V&V, albeit with a requirements model. So there's plenty of information out there, and we thought it was possible that we'd be able to collate this information and pitch it in a way that made sense to people interested in model-based systems engineering. So our approach had two strands to it. One strand was a literature review, where we looked at the literature available to us and tried to distill that down. And we also did a roundtable with current MBSE practitioners. Not only did we use the MBSE practitioners to give us advice on what they were doing in model-based V&V, but we also used that for trying to assess the needs of model-based practitioners as well. Find out what the concerns were for them and what they had trouble with and what they wanted us to answer. For the literature review, we took our own collections. Most of the books that I've already mentioned on the previous slide, I have copies of, so that was my first port of call to look there. We also did search in several online catalogues, Google Scholar, ResearchGate, and the Wiley catalogue. As I'm sure you're aware, the Wiley catalogue has got articles and papers from INCOSE journals and conferences in it. We used a standard set of queries. We queried for either model-based systems engineering as an initialism, so MBSE, or we used the term in full, model-based systems engineering with and without a hyphen. We also then used one of the following words, either verification, validation, check, testing, inspection, or review. As you would expect, we did return a rather large number of papers from doing that test. In fact, I think initially we had somewhere in the region of 600 possible papers to include, which is obviously far too many for us to manage. So we then had a multi-stage process to reduce that down to a manageable number. In the first pass, we simply looked at the titles and decided whether or not we felt they were in scope. After we used that to narrow down the set, we then looked at the abstract from the papers and used that. Then with a much smaller set, we skimmed through the papers and made a decision there whether to include them or not. And then finally, for the smallest group, we read the papers in full and made a final decision on the ones which we thought were applicable. Finally, at the end of that, we were left with a list of 22 books and 23 papers, which was still a rather large amount of material to read, but we managed it. That's the good news. And if you're interested in seeing the papers that we included and the books we included, then a full list of those are available on the MBSE wiki, and there is a reference to that in the actual paper. The roundtable took place at a meeting of the MBSE interest group on the 26th of March 2019 in Bristol. There were 25 members present, representing 17 different organisations. In some senses, that does seem a long time ago, March 2019, a different world perhaps. But if you know anything about the way that working groups operate, this is actually quite a quick turnaround for publishing information from it, so we're quite pleased about that. The seed question that kicked off this whole activity was proposed by Rolls-Royce, and I think it was from reading the minutes, do you have any advice on best practice for model review validation? So it was quite a general and very open question that we kicked around in the group, and that helped us to identify not only what people thought were good practice or best practice, but also it allowed us to scope the question a bit better, because some people said, well, that's interesting, but it's not the only thing that we should consider. You'll notice that the title of the presentation does not completely reflect that question. We've changed it from best practice to good practice, and that's simply because we haven't got any quantitative research on the relative effectiveness of the various techniques. So we can't say this is the best thing to do. We can just say these are all things that people do and have had success with. We recorded the output of that discussion as a mind map, and I'll show you the mind map in a moment. And then we went on and we did a little bit of analysis, and we created a use case diagram from the mind map to explore the question of why should we review the model further. We appreciated during the discussion that there were different viewpoints here about why we should review the model, and it was worth exploring what they possibly were and what were the advantages. And as mentioned, both of these are available on the MBSE wiki, and there is a reference in the paper. So here's the mind map, and I appreciate that it may be too small for you to read in detail. The idea is not for you to review the mind map, but obviously to give you an idea of what it looks like, its format, and for me just to give you a little bit of a background behind it. So as I said, the interesting thing about recording this information in the mind map and also performing a little bit of analysis on it is we realized that although the seed question was about review validation, it quickly became apparent that there were other areas that we needed to be interested in. So not just validation, but verification, not just review, but there were many other techniques which you can use to improve the quality of your model. So that was our initial input into this activity, and it was helped frame the problem initially. So then this is the use case diagram. This is a little bit more readable, hopefully. This explains around the question, why do we review the model? When we started out, we thought the primary motive for reviewing the model would be to increase the model quality. That seemed to us to be the most obvious thing, the reason for doing it. But it also became apparent that there are some other great advantages for reviewing models, which may not necessarily be immediately obvious. One of the advantages to reviewing the model is it's a great way to transfer knowledge. Because you force people to review the model effectively, you have a process which means they have to read the model, they have to discuss the model, and they have to comment on the model, then it increases collaboration. It's a great way of transferring knowledge between people. And that's in both directions, of course. People will find discrepancies in the model, and that will inform the modelers, but also people reviewing the model will be informed by the model. So it's a great way of knowledge transfer. It's also a really useful way of assessing the progress of the model. So you can collate metrics from your review process, which can tell you things about the completeness and consistency of the model. So for instance, the difficulty in reviewing the model gives you some indication about its complexity or its understandability. And that's really useful to know because you can use this information to focus your V&V effort. Also, the amount of defects that are found during a review process tells you something about the quality of the model. So these are all really useful things from a project management perspective, not just from a quality assurance perspective. Okay. Let's now consider the purpose of verification. One of the comments that came out and is captured in the mind map was noted that we need to be very clear about the difference between verification and validation, and these two things are often confused. ISO 9000-2005 states that verification is the confirmation through the provision of objective evidence that specified requirements have been fulfilled. Okay, so what we're checking there is that there's some sort of defined traceability between the requirements which have been captured and any transformations within the model. Does the model accurately represent the requirements or a solution to those requirements? ISO IEC IEEE 15288 2015 goes on to say that the purpose of verification is a set of activities that compares a system or system element against the required characteristic. This includes, but is not limited to, specified requirements, design descriptions, and the system itself. And we have this great phrase for summing it up, which is the system was built right. Did we correctly follow the process? Is it a valid transformation? The INCOSE handbook goes on to clarify this further by saying that the verification process can be applied to any engineering element that has contributed to the definition and realization of the system itself. What that tells us is that since the MBSE model is an engineering element, it can and it should be verified. And there's no surprises there. There was consensus around the table that that's something that should happen. Why do we bother doing this with the model? Why do we bother doing verification? Well, obviously, it all comes back to the left shift principle, which is a well understood principle within systems engineering. The purpose of performing V&V in the model is to detect and reduce defects early within the life cycle. And we know that the earlier defects can be identified, especially before the realization of any physical system element, the lower the cost and complexity of rectifying them. And there is consensus throughout the literature on this point. There are no dissenting voices on the principle of left shift. What this means in practice inside your model-based systems engineering model is that you have to ensure that transformations within the model are logical and correct. The kind of transformations that we're talking about are the transformation from the problem space to the solution space. So does the solution actually does the solution actually satisfy the problem? Transformations from black box representations to white box representations. So having defined a black box element, its interface, etc., does its behavior then correctly implement that interface? From higher abstractions to lower abstractions, so moving from levels of requirements, for instance, is that logically incorrect in that transformation? The mechanism to use such a progression is generically called traceability. We use the term traceability all the time in systems engineering. And the SysML language includes several types of traceability for particular relationships. Excuse me a moment. So we have the concept of derivation. So derivation exists between requirements. So you can derive a requirement, say, for a system requirement to a subsystem requirement. And that's a relationship between requirements. There's a relationship called satisfaction, which is from element to its specification. So I may say that a system element specification, as represented, say, by a block, satisfies a requirement for that block. There's a refinement relationship, which again goes from a less precise element to a more precise element. So for instance, I may take a system requirement and refine it with a use case being a more precise way of specifying that requirement. There's a concept of allocation. Allocation allows me to allocate an element in one viewpoint to an element in another viewpoint. So an example of that may be that I have a viewpoint which defines a function, and I allocate that function to a structural unit, I say a block again. That allows me to separate out concepts such as function and form. It allows me to define the functions first independently of the form, and then allocate those functions to the form. There's also a relationship called verification. This is often misunderstood in SysML. Verification is allowed between a test case and its subject, and it doesn't say that the test case proves that the subject has been verified. It simply says that the subject, in this case, the verification, will, if correct, prove that the test case verifies the subject. So it's often misunderstood there. And then there's a generic relationship called traceability for all the other cases which haven't been covered. Okay, so we have these various mechanisms inside the language to show this principle of verification from one element to another. And effectively, that's what we're doing. We're using traceability to show these relationships. So thinking about what we're doing there in general, we put together this generic verification process. Okay, so what we said is that for any element, or for each element being verified, there were 3 steps that you had to go to. The first one, step 1, was to ensure that the element was internally complete consistent. So before we even attempted to show that it was a valid transformation from a preceding element, we had to prove that it was actually a valid element in its own right. Is it complete and consistent? The challenge here is that completion and consistency varies throughout the life cycle of the element. So if the element is a black box element, then it's complete and consistent when its interface is complete and consistent. However, if it's then a white box element later on in the life cycle, it's only complete and consistent when both its interface and its internal specification are complete and consistent. This means that you may have to revisit an element multiple times during the V&V process. Having ensured that it's internally complete and consistent, the next thing, step 2, is to ensure that it's traced from a valid specifying element. And where it isn't traced from a valid element, you have to determine one of 3 reasons. The first reason is that the relationship is missing. It should be traced, but simply we haven't recorded the relationship. If that's the case, you can add the relationship and move on. The next reason is that the specifying element is erroneously absent. An example there may be, you know that there's a feature required, but you don't have a requirement for that feature. If that's the case, obviously you would go back to the stakeholders and confirm that that requirement is in fact needed. You would add the requirement and then you would create the traceability. And then the third reason is that the element is redundant. This is the case where there is no requirement for it, and that's because the stakeholder doesn't have a need for it. It's ended up there by mistake, in which case you would remove the feature. Okay. Having done that, you also need to check, which is step 3, that the kind of traceability is appropriate for the 2 types of element. Obviously, if you don't have any flavors of traceability, you simply have a link, then this is not needed. But in languages such as SysML, where you have different types of traceability, you need to ensure that you've used the right sort of traceability. Possibly more important is to record the rationale. It's important to record the rationale, although it's not easy to record the rationale for a couple of reasons. The first is that by forcing yourself to write a rationale, it makes you test your logic to see whether or not the argument you're making that the system element is a valid transformation of another system element is correct. It forces you to test that. Now, having recorded the rationale, it also makes the review process much easier because it explains to the reviewers why you came to that conclusion. And also, it's a really good way of you not going over the same work more than once. If you don't record the rationale, every time you revisit it later on, you're likely to have the same conversations again, where somebody says, why have we done that? Why do we think that's a valid transformation? If you've recorded it and you have the reasons for it, then it's easier to have that conversation. You can move on. Okay. Let's now move on to the purpose of validation. ISO 9000-2005 says that validation is the confirmation through the provision of objective evidence that the requirements for a specific intended use or application have been fulfilled. ISO, IEC, IEEE 15288-2015 says that a system is able to accomplish its intended use, goals and objectives, i.e. meet the stakeholder requirements in the intended operational environment. The right system was built. While verification is an analysis activity which can be done by comparing separate elements in the model, ultimately validation can only be performed by the stakeholders. The model is validated when all the stakeholders have confirmed that their model represents their requirements. So people have to be able to read the model. That's the bottom line here. It's no good for the SysML experts to say that the model is valid. They can't make that assertion. People have to look at the model and say, yes, the requirements that it captures are valid. Again, this is based on the left shift principle. The earlier that we can find defects here, effectively, the earlier we discover we're solving the wrong problem, the earlier we can make corrections, and it's easier and less complex to do them and cheaper to do it. There are a couple of risks here, of course, which is that because this is based on the say-so of the stakeholders, the earlier we do this, the more time they have to change their mind, particularly as the system develops. So we may give them an early representation and say, is this correct? But then as the system evolves, they may start to change their mind, or it may be the environment that the system is going to be deployed into changes. So there are some risks that we have to manage there. And so it may not be sufficient to perform validation once and never do it again. You may have to revisit validation, or at least revisit your assumptions to check whether or not they still hold. Let's look at the various types of verification validation, the mechanisms that you can use to employ these. These all come from the INCOSE System Engineering Handbook, which initially lists 7 different techniques. So the first technique is inspection. Inspection is a visual examination without any stimulus. So effectively, you're just looking at the system of interest to see whether or not it looks the way you expect it to look. Okay, in terms of a model-based systems engineering model, that means reviewing the model effectively. Okay. We also have analysis. So analysis based on data, probability, logical reading, modeling and simulation is a way of looking at the model and its metadata and making arguments about whether or not it is completely consistent. So the generic process that we talked about previously for doing verification is an analysis process, effectively. We then have 2 ways of looking at behavior. There's demonstration, which is about showing the operation in a generic way. So does it do the kind of things you expect it to do? Does it include the sort of things that you expect it to do? And that's subtly different from test, which is about showing operation in a precise way. So with tests, you have a controlled environment, you have a set of test steps, you record results, and ultimately you have a verdict about whether the test passes or not. Obviously, they cover different aspects of the system. So while demonstrations are perhaps broad and shallow, tests tend to be narrow and deep. And of course, you can't cover the whole behavior using test. It would be nice. And so demonstrations can be equally as useful, and the combination of those 2 things are useful to have. Clearly, if we're looking at a model, then demonstration and test is demonstration and test of a simulation. The model itself doesn't have a behavior, it has to be interpreted. The next type of verification validation is by analogy or similarity. And this is based around the argument that A is a kind of B and B is verified or validated, and therefore we can assume that A is verified or validated. Because the MBSE model is not the system itself, it is not the system of interest, it's an abstraction of it, then technically all the V&V techniques we're talking about today are types of analogy. Because what we're saying is that if we know that the model is verified and validated and the system conforms to the model, then we have a high degree of confidence that the system itself will be verified and validated. Okay. There's some big ifs in there, because I appreciate that you have to then prove that the model conforms to the system of interest and vice versa. But that's the argument that we're trying to make. Simulation is listed as a separate technique, and that's the primary mechanism for model demonstration and test. And then it also lists the technique of sampling. Sampling is similar to analogy in that it says, because we can't test anything, if we test a subset of all the things, as an example, we can draw conclusions from that subset based on how big the subset is of the whole population and various other factors. And again, that's a really useful technique, even when it comes to the model, because we probably can't test everything. And so we need to focus our efforts on those things. Just to confuse things, the handbook then goes on to say that analogy and simulation are types of analysis. So there's probably only 5 different types, not 7. Okay. I'm now going to hand you over to Alex, who's going to talk a little bit more about the types of model and model view.
Thank you very much, James, and good morning, everybody. James just talked through the different types of verification and validation, but it's important for us to consider the types of model or model view that we want to assess, as this could have an impact on the technique that we're going to be using. All of our SysML diagram types can be classed as descriptive views. These are just being used for communication, but they can be reviewed or inspected. Our parametric diagrams fall into the static analytical type of view, and as they're event independent or stateless, we can actually start to solve these. Our sequence, state machines, and activity diagrams are all in the dynamic analytical type, and they're time event varying stateful, and they can be simulated. Okay, we've already said that descriptive views can be reviewed or inspected. Generically, this is the process of manually checking a product or process artifact by a group of people. The terms have no fixed individual definition, but systems engineering treats them as overlapping and interchangeable. However, if we look at the software engineering field, inspections are specifically formal types of review and include multiple process steps and meetings. One example type of formal inspection that could be used is the Fagan inspection process, which has defined steps to complete the inspection. I think it's interesting because it has both entry states, which are defined, or entry and exit states, which are both defined in a high-level document. And so we can check if an item meets the standard to warrant an inspection, and then that it meets the standard to pass the inspection as well. It defines a defect as a non-compliance of the exit state. The process goes through multiple steps, which includes planning, preparation, an overview where everyone's educated in the item. People do individual checking of the items to be inspected, and then they get to the actual inspection meeting itself, where the defects can be identified. This is then followed on by any rework, which can loop back to the planning stage until all the defects have been remedied, and then the final stage is a follow-up, which is actually the verification that the rework is satisfactory. Regardless of the use of the terms, it's agreed that the effectiveness increases with formality, but then so does the cost. From the MBSE working group discussion, we realised that less formal review techniques can be used more frequently, and reserve the more formal methods for milestones or areas of high risk. Final point is that it's important to remember that reviews or inspections are not just about cleaning up, it's the act of measuring and validating the technical documentation, which can even be the diagrams. Okay. Inspections have their own set of challenges, which actually increase when we include the MBSE and SysML. We find that culture can prevent effective application of inspections, especially in organisations that have not been previously done inspections or reviews. This can be found as a fear expressing or receiving feedback, and this can be amplified when silo boundaries start to be broken down, or when culture makes it difficult to accept criticism. We can start to mitigate this with appropriate processes and training that show it's not about stick bashing, but about product improvement. It's also important to remember that inspection is not criticising the work, but critiquing it. The important difference here is that criticism is identification of negative aspects and faults, whereas critiquing is identification of both good and bad points, so it enables us to celebrate our successes, as well as increase the quality of our output. We also have challenges of effectiveness and efficiency, which can raise concerns such as, are we achieving the right level of quality? Are we spending an appropriate amount of time on the review? Are we nitpicking? Are we playing lip service to the inspection? And are we being consistent between reviews? All of these can be met with a suitable use of standards. So from MBSE, we can include architecture framework and patterns, but we mustn't forget simple things like checklists. Next point is our language for MBSE, because often that can present challenges with different levels of understanding between the modelers and reviewers. We could try and achieve the same level of understanding through training and experience, but we realistically think this is impossible. So we can do different views during the construction compared to analysis and reviewing. We could even use a different format. The last point in this slide is that as models are multi-dimensional with many potential paths of analysis, how do we know where to start inspecting and how do we know when we've reached the end? Models aren't like a book where you have a start, middle and end. So we can actually define storylines within the models as inspection routes or inspection scenarios. Analysis is slightly different to inspections as this is executed by individuals rather than wider groups. For MBSE, we typically include syntactical rule-based checking, such as language compliance, which is equivalent to spell checking the syntax of our models. This isn't an easy task for a human to do reliably and only provides low to moderate effectiveness if it's done that way. However, it's a task that's easily automated, just like with our spell checkers. It's also a valuable step as it's a prerequisite to any simulation which will require a well-formed model. Formal model checking can help identify defects, such as dead ends where we have states for logic to get stuck. We can have unreachable states where we put all the effort in to find them, but we're never actually going to realize them in the state machine. But actually, my least favorite from experience is the race conditions or race hazards. So with a simple inspection, everything could look fine, but when we add in timing or latency, we can often get some unexpected or wrong results. The challenge with formal model checking is it often requires translation to another modeling language and can be difficult or expensive to implement. This again means it's often reserved for high-risk aspects such as safety. Metrics are another way we can analyse the models, and they can be calculated for things like complexity, coupling, cohesion, completeness, stability, and understandability. Looking through these, we find that coupling and cohesion are useful for analysing our architecture, as we want high degrees of coupling, so linking within a family, and low levels of coupling, so relationships between the families. One way of measuring this could be using an n-squared chart, which can analyse the connections between elements. Completeness is interesting as it's context-specific. We can imagine something's complete at a concept gateway would not be complete at a detailed design gateway. It's also interesting to look at completeness alongside stability. We might find a stable model which is lacking in completeness, and so no one's working on it even though it's not complete. We have a couple of example metrics on this slide here, and we can use these to prioritise our work to get the best value out of the less shift of effort. The heat map can be used for things such as defect densities. We could have architectural layers on one axis and subsystems on the other to identify if a particular subsystem is more defect prone than others, or if our defects related to a particular architectural layer, for example, more defects in the white box model compared to a black box model. We might find hotspots on the heat map, or even links to the capabilities of the people working on the model, so then we can prioritise where to offer training or support. We could even use the axes for diagram types against subsystems to analyse for defects in these areas, or we could actually categorise the defect types themselves and feed this into the heat map. We've already mentioned stability, and model chair and S-curve is a good example of how to analyse stability. If we just go back to the previous slide, James, just to see the curve there, thank you. You can use this as an indicator that's a suitable time for an inspection. So when the rate of change is flat, so like at the end of the curve there, there'd be a good time for inspection. We could also identify if the model is still changing at a gateway, so it might be a high rate of change. We might be able to identify if this is due to defects being corrected, or maybe we can identify they're actually over-modeling if we have a high level of completeness. Moving on to the next slide with simulation, this allows us to experience and interact with the model through different interfaces, more specifically one that's more natural to the thing that's being modelled. This could be as simple as annotating a diagram with the current or previous states. We might have a rich user interface with familiar icons and controls, or we could even extend it to driving virtual worlds, controlling hardware and software in the loop. Really what we're trying to do here is provide a virtual demonstration of what the model is representing. This puts into the context that many stakeholders will be familiar with and bridging the language barrier that our modelling can create. As simulation gives us the ability to drive the model through different states and operating scenarios, we can also use this to help solve the challenge of identifying the inspection paths through the models. It's often possible to simulate directly from the model, so we can have full traceability then from the stakeholder requirements to the elements being simulated. It also helps to reduce the risk of manually introduced errors when separately building simulation from the model. and we also reduce the need to validate and verify the model itself. Simulation doesn't just have to be for the requirement stakeholder though. On a small scale, we can use it for unit testing, and we can also automate it for regression testing. It can be part of our formal test processes, where we Google it by someone else other than the model. Parametric solving is not really simulation in its own right, but an expression of the output of model parameters, and we can include this as part of the simulation. Also, with the output being a particular value, we'd need to perform reviews and analysis just to check that the values can be correct. It can be difficult to verify parametric equations when they have vast number of inputs and outputs, but we can compare them against known solutions or another model that's built to the same specification but with a different design. We have to be careful though, just to make sure that we're not just identifying differences for when we don't understand what the differences are or the location or their nature. I'll now pass you back to James, who's going to take you through our recommendations.
Oh, don't know what happened there. Yeah, so we came up with a number of recommendations based on the research. Obviously, these slides only give you an overview. There's more detail in the paper, and in fact, I'll talk about that further in a minute. So our first recommendation regarding reviews is that you should have a formal review inspection process. You should perform this at significant milestones. And although we haven't given any guidance on what format that process should take, we do mention the Fagan inspection for software as a good starting point for these things. You should also review the model informally and frequently between milestones. The difference between those two things there is that the formal review is part of your process, whereas the informal review is just good model craftsmanship. You should give your reviewers access to the model, not just the diagrams. And the reason for this is there's a lot more information in the model than just in the diagrams. Also, it would be counterintuitive to have a model-based approach and then a document-based review process. So you should have specific viewpoints to aid the review process. You should record the review comments in the model. You should record all the information about the review in the model. You should provide the reviewers with metrics about the model. This allows them to focus their efforts, where to spend more effort and less effort on the model. And you should regenerate metrics from the review itself, because that tells you things about progress of the model, its maturity, and those kind of things. You should use an architecture framework. This allows you to write criteria which determines whether or not a view is complete and consistent. You should have define a modeling standard. Does the model fulfill the standard required by your organization? And you should use modeling patterns and check for anti-patterns. And there are some sources for those which we give in the paper. Where appropriate, you should use checklists. Checklists are a great idea. If you've ever read the book, The Checklist Manifesto, you'll see that they've had great effect in things such as medicine and surgery, and they can be equally as effective in systems engineering. Something wrong there with the slides. You should perform analysis on the model, so check it, the syntax of the model. It's very difficult to do syntax checking manually, so you should automate that as much as possible. You should collect metrics on the model and the VMV activities that we've already mentioned. Wherever possible, you should do simulation and parametric solving on your model. This demonstrates behavior to stakeholders early and often, and it allows you to build a shared vision. So this is the demonstration element that we talked about previously. And as well as the demonstration element, you should test the model, and testing should be a formal activity. You should define formal test cases, you should control and review them, you should automate it as much as possible to perform regression testing. Okay. Clearly, this is not everything that we could do in this area, so we have identified some areas of further work. There's been some recent papers published on this subject. A very interesting one has the title, Is Verifying Frequently an Optimal Strategy? So we'd like to review that and include the conclusions from that in our research. But also, and we've already had this discussion with interested stakeholders, we think we should provide more detailed guidance on some of these specific areas, particularly the inspection process, what we regard as being inside a modeling standards, what's needed, the application of checklists, and possibly quite importantly, metrics about how you collect them and how it's useful to analyze them in this process. Apologies that I rushed through the last few slides. We seem to have overrun in time.
Thank you, James and Alex. We've just got a little time to ask some questions. We've got a few, so there may be some that you can take on after this and answer them by correspondence or however. One from Derek Price. Do you think we have a potential gap with respect to validation, i.e. fit for purpose, of the modelling effort itself for the customer person in addition to the scope of validation presented for the customer person paying for it?
Well, I think there's always a danger that there will be a mismatch where there isn't a lot of involvement of the customer. So as I mentioned right at the very start, there have been quite a lot of model-based endeavours which have been remote from the customer and even remote from the other systems engineering activities. And I think whenever that's the case, there is always a danger that it won't be fit for purpose in that sense. You should always have a mindset of what is the value of this activity and what is the risk that this activity is trying to mitigate. Systems engineering is a risk mitigation strategy. And so you should always have that in mind. And that should be equally true for, if not more true, for a model-based endeavour. And so I think Derek's absolutely right that you need to really focus on that and work out what is the value that you're adding by doing these activities.
Okay, thank you. Douglas Craig asks, do you have any case studies demonstrating good practice or indeed the opposite?
So most of the literature we referred to has got case study information in there. The case study information is always slightly, less effective than you would like. And the reason being is that people tend to argue that either the project that the case study is based on is not like their project, or the environment that it's in is not like their environment. So people are always kind of reluctant to take lessons from case studies, but there are case studies. And also with the negative cases, they're less easy to find. The reason being is that unless it's been a complete disaster, usually with the loss of life, these things aren't published. Organisations tend to put a positive spin on projects, and they're very reluctant to admit when things weren't quite as well as they hoped they would be. But again, there is some information on there. The other thing I would say is that it's not usually specific to model V&V, it's usually papers about modelling in general. And so the V&V aspect of it tends to be only a subset of that.
Okay, Georgi Markin asks, how do you perform V&V in an agile-based development?
So V&V in an agile-based development, obviously the iteration cycles are as short as they possibly can be. Again, you have to do it on a risk-based approach. So you have to look at what's the minimum you would want to do in order to reduce your risks to your risk appetite. But of course, the other thing about V&V in an agile-based way is that you want to show effectively a product to the stakeholders in each iteration. And so there's much more emphasis there on the validation part than there is on the verification part. And so if you've got simulation model, if you're able at the end of every, say, sprint, if you're using Scrum, if you're able at the end of every sprint to show the simulation to your stakeholders, then they will tell you whether or not it's doing what it's supposed to do. Obviously, that's demonstration, and so that only gives them a broad confidence in the model. You still need to be able to perform some testing to get to know that it's doing precisely what it should do. But that's where it becomes really important to do automated testing, because in very short cycles, it's not possible for you to do manual testing. You need to be having the tool testing your model every night after every change.
Okay, thank you. I think we've got time for probably one more. Stephen Powley asks, storytelling is increasingly popping up on my radar as valuable in engineering. Can you give us an example of how you've used this in practice for model V&V?
Storytelling. So Stephen's absolutely right. So there are various types of artifacts in a model-based model. Some of them are very dry and specific and almost mathematical. And clearly they're not the ones that you want to put in front of your stakeholders to express what you're trying to get across with your system. So the storytelling element comes through scenarios, and again through simulation. So you can demonstrate scenarios to show them that the system is behaving in the way that you want it to. There's this disconnect, isn't there, which is that the stakeholders are ultimately interested in the final system, but they're not necessarily interested in the engineering process that got you there. So they're less interested in the verification and they're more interested in the validation. And so validation has to be through a storytelling approach.
Okay, thank you. So once again, thanks to Alex and James. We're right out of time, so the next session will begin at 11. Thank you very much.